from a positivist point of view, which basically means mainstream scientific type experimental research with results and statistics and what have you, rather than interpretivist research, which is largely qualitative. So just to put that in perspective, let's go straight to a presentation. Just make sure that it really does show. Right, there we are. Okay. Analyzing your data. Understand what you have done. Okay, and I've used this famous quote you might have heard of. It actually comes from a poet from a couple of 100 years back. Fools rush in where angels fear to tread. In other words, racing in and just drawing the most obvious conclusions from your data without the deep reflection, thinking, arguing, discussing with other people that's actually necessary, not only to avoid mistakes, but also, in fact, to bring out the most interesting and exciting things that might be sitting in your results. I'll give examples. The first thing, however, is to prepare your data. As with anything else, if you want to do your best work, then you're fully prepared for it. I spend quite a lot of my time assisting students to go through their results. And typically, we end up spending at least the first few days just trying to get their results into some sort of useful format that can actually be analyzed. Let me give some examples. Right. Sorry about that thing that's appeared in the middle. I've overlooked that for the moment. My first point there was avoid losing data through summarizing things, okay? Summarizing might be that you come along and present a mean and standard deviation, minimum and maximum that you've already calculated somewhere else, some other spreadsheet, but you don't actually bring along the data. And the second, an extremely common one, is that you lose data through coding. By coding, what I mean is you take groups of patients and give them a code. Doctors have got a horrible propensity to do this. For example, instead of saying the age is 37, they divide the ages into 10 to 20, 20 to 30, 30 to 40, 40 to 50, and write that down instead. I think some of them actually think that that sounds more scientific or something like that. In fact, it's not. And I'm going to show why that is so. So here's an example, right? There is the data you do in a study, okay? Many more rows than that, but basically on a whole lot of people, you measure their height and you measure their body mass. And your hypothesis is that as people get taller, so their body mass increases. So far, so good. But now you succumb to that temptation I've just talked about. So you divide up into the 141 to 160 centimeters, the 181 to 200s, and so on and so on. And then you code that. So now we have group B, which is 160 to 180 centimeters, group D, which is 200 to 220 centimeters, and so on, all the way down. And then the sad thing of all, you may actually go back and delete that original column of heights, gone forever. We can't retrieve it. And now you want to analyze your data. Well, this is the best that you can do, okay? Group A, Group B, Group C, Group D. There's the mean height of Group A, mean height of Group B, and so on. And yes, you can see it seems to tend to rise. And the appropriate statistical test to compare them is called ANOVA, analysis of variance, and it is significant. However, if you had just stuck to the original heights, this is the graph you would have produced. Again, using a different test, Pearson's R, you would have found that significant increase in mass with height, but there are all sorts of other very useful bits of information you could derive. That R value is an indication, as is the R squared, of just how predictive height is of mass. R squared here tells us that you can predict 25% of your mass through height, but there's another 75% that is not predicted from height alone. So I think you'll all agree with me. Just looking at that graph, that's an extraordinary rich graph, and that's an extraordinary impoverished weak graph. Okay, so in fact, by reducing the amount of data by coding, you have lost valuable information. You have made your results weaker and poorer than if you had just left it. So in preparing your results, keep all your original data and don't discard data because you've summarized it as means or put it into groups or codes or something like that. And in fact, you can take one step back. When you collect your data, collect all the data, don't impoverish it. So for example, in a questionnaire or a data sheet for a patient should say age, and the person fills in 59 or 34 or 62. They should not fill in a tick for 20 to 30, 30 to 40, 40 to 50, etc. That's what I mean by maintain your data and don't weaken or impoverish it. Simplifying your data has led to a loss of data. Always work from original data, okay, and bring original data to the statistician. Don't replace the original data with summarized things, age groups, averages, totals, etc. The second thing is format your spreadsheets correctly. And I find that many of our students don't understand the concept of a spreadsheet and how it should be used. And they think it's just another form of Word document, except you write in little rectangles instead of on lines of a page. And you can beautify it and make it look pretty. But that is not the purpose of your spreadsheet when you collect and analyze your results. Okay, the data has to be presented in spreadsheet format so that it can be manipulated mathematically and statistically. You can't bring your data in a Word table or in a printed page or in a PDF or a PowerPoint slide. The data has to be analyzed in an Excel type spreadsheet, preferably in a single workbook, using as few worksheets as possible. So if it's possible to get all your data onto one sheet, you do so. That's what's required for statistical working. Having to find some data on the second sheet and other data on the third sheet and yet more data on the fourth sheet makes it extremely difficult to analyze anything and very, very prone to errors creeping in, links being lost, things being missed, and so on. So one of the first things we often do when I sit with a student and help them is we spend an awful lot of time moving things from Word back into Excel, from second, third, and fourth worksheets on Excel back onto a single worksheet, and so on, and so on, and so on. Right. There should be nothing on that worksheet except data, okay? And by headings, I mean the column headings, the variable names. I don't mean headings like results as analyzed on the 24th of June. Not that sort of thing, not a title. Only the data and the column headings. One row per subject, which means you don't leave blank lines to look pretty or put little lines or colored lines in between people. One column per label or recorded variable. And hello?
Hello, hi sir. Samuel again from Academy Family Services.
Yes.
Can you do me a favor and have a look at your WhatsApp? I'll send you through invoice.
Thanks, I'll do that. So I'm just in a meeting now. I'll have a look shortly.
Okay, no problem.
Thanks. Sorry, I thought I'd better answer that just in case it's one of you calling me to say that my PowerPoint has disappeared or I've gone mute or something. It was actually the plumber, so I apologize for that. Let's go back to PowerPoint. Right. One usable item of information per cell. That's how we analyze things. Okay. Right. We're going to turn to a few examples now. Okay. Here is a spreadsheet. Somebody's tried to make it pretty. In the first line, they've written study outcome December 2021. Is anything wrong with that? Looks all right, doesn't it? Until you come to analyze it. Now I want to choose my variables to analyze, and it says the variables are 2021, December, outcome, and study, because those are the words written at the tops of the columns. So all Statsware, including mine, thinks that December is the name of the variable of which each of these things is an example. And it thinks age is just one data point, along with 36.6. And it thinks drug name is just a name like phenobarb or valproate. It doesn't recognize that it's a variable name. So having made the thing look pretty like this has actually introduced problems and potentially errors into the analysis. I'm going to give examples of that right now. Okay, so here is a spreadsheet. It's got horrible things wrong with it if the intention is to analyze it. Okay, we're going to see, in fact, we've already seen that that introduces serious errors. Okay, ID, age, experience, etc. should have been in the first row. We're going to see that there are serious errors introduced by putting the totals, means, standard deviations, anything else you want down at the bottom of the columns. If you want to do that sort of analysis, you make sure you do it on a different spreadsheet to the one you bring for statistical analysis. And I'll show you why. We're going to see there are horrible problems implicit in the way in which the data has been entered into those cells, and also the way the data has been entered into those cells. And I'm going to illustrate each one of those right now. Right. So here we are. We're just summarizing the age of our subjects. Immediately, we notice some serious problems. Okay. The mean age is 201 years. The maximum age is 2018 years. Nonsense. The fact that it says 2018 gives us a hint what's going on. Our software has analyzed the age column and it's seen a number 2018 there. So it's regarded 2018 as an age, just like 33, 39, 30, 36, etc. And it's incorporated it into the statistical analysis. So having made the thing look pretty with a little thing saying September 2018 has totally distorted the analysis. Is the first problem. Right, that should not be there. Second problem. I've got rid of that now, but now it says the maximum age is 485. What on earth is going on there? Well, that's the thing you wrote there as a total. Okay, my spreadsheet, the analysis thinks that I have subjects called A1, A2, and so on, all the way to a subject called total, whose age is 485. So it's incorporated that into the analysis. So that now has no place there at all. This total and average cannot be on the same spreadsheet that we're using for analysis. Now we've still got another problem, even when we put that right. It says my N is only 12. To me, it looks like there ought to be 21 subjects, okay, in that little spreadsheet on the left. If I count down here, in fact, there are 12 here from 46 to 40, but it's discounted all of these from 37 up to 33. This may not be immediately apparent to you, but you can see they formatted differently. These are all on the left. These are all right aligned. And what's happened here is that these have been inadvertently formatted as text, not as numbers. In other words, the program thinks that this is not the number 33, it's the letters 33, okay, equivalent to THIRTY hyphen THREE, okay? And you would never enter in words 33 into a calculation and, for example, multiply it by the digit 12, okay? So it's regarded it as text. It thinks it's just another word, so it's excluded it. So this can be a very tricky one. It can easily trap people, and I won't go into what you have to do about it. But this has to be reformatted, not as the word 33, but as the number 33. And as soon as we do that, you can see it's now all nicely right aligned because it's seeing it all as numbers now. This number pops up to 21. So now 4 or 5 steps later, we've actually got an accurate analysis. Now, in this particular examples I've been using, it was fairly obvious that something was horribly wrong. But if you've got a data set, of many subjects, 60, 70, 80, 100, 200, 300, it's very easy for quite a large number of these to slip through. And you won't even be aware that quite a number of results have been excluded or have been included when they should not have been. So when you do the analysis, you always have to look at the number that were analyzed by the software and just make sure it actually makes sense. So you can see how the way you enter your data into the spreadsheet can have a major effect on the analysis that's carried out. The spreadsheet is there to feed the statistics. It is not there to look pretty or to dish out to people so that they can admire your results with pretty titles and headings and colors and spaces to make things easier to read and so on and so on. This is what you want. Okay. Columns with a variable name at the top. Rows, 1 row per subject. Cells, each one with a single result for that variable. You'll see there's a blank here, and we'll talk about what that means later. Okay, now let's turn to the next column. If you're looking for an average age, any program, whether it be Excel or any statistical program, is just going to ignore 4 years, 6 months, because that's not a number as far as it's concerned. Okay, nor is greater than 50. That's not a number. Nor is 204 months. That's not a number. So when it does the analysis, it'll work an average of everything there that looks like a real number, but it's going to omit anything that's got words in it or that's got symbols like greater than in it, etc., etc. So you have to be extremely careful how you enter your data. You can't use words like years and months and equal signs and minuses and greater thans and so on and so on. Now here's the next problem. Okay, here we've analyzed the students in a particular medical school in South Africa. Okay, and we are looking for some sort of results, some sort of score, and we've analyzed them by school and by gender. This is just, the start of the spreadsheet. Now, a very obvious thing to do, isn't it? Is just get a breakdown of our subjects by university and by gender. We're looking for something like this. From NMU, 2 were female, 1 was male. From UFS, 1 was female, 5 were male. Simple. Look what my statistical software is going to make of that spreadsheet we offered it. Meaningless. The reason is it has seen .WSU as different from WSU. It's seen NMUni as different from NMU. It sees Free State as different from UFS and different from FS. In this particular case, my software has not distinguished uppercase from lowercase, but in many cases, statistical software will. It'll regard UFS and capital letters as a different place to UFS with small letters. So you can see that this inconsistency has led to a total mess, and the same here. It does not realize that F, female, female with a full stop, all mean the same thing. So it's regarded them as separate classes. So in order to overcome that, we have to make sure that we use the same term every time for UFS. So if we choose all caps UFS, then this one should have been all caps UFS. 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 And when you do that, you get a totally well-behaved result. And you see, I've settled on F and M. I could have settled on female and male in words as long as I used the same one every time. I could even have used numbers 1 and 2, but that's for another day as to when it is appropriate to replace classes with numbers. Some people just automatically doing it thinking it's good stats. Well, it's not, but there are some instances where it's appropriate. But the important lesson here is be consistent, because otherwise the analysis is going to see things as different groups, even though they are one group. Right, and similarly with this sort of thing. So often people have put this in their spreadsheets. It's got a height of 167, 148, 180. Number 5 didn't come for his appointment, so somebody's put 0. And then they put the words not done. Somewhere else they put a question mark and then an N/A for not available. None of those things, not done, question mark, N/A, can be analyzed by a statistical program. So at best, they are just bounced out and not used. At worst, they actually gum it up and they are interpreted wrongly, or they flag error messages. But that's not the worst of this. Okay, look at my summary. It says there are N subjects. In fact, there are 1, 2, 3, 4, 5, 6, 7. It says the minimum is 0, and it's calculated a mean of 130. And the reason is it thinks 0 means that subject D had a height of 0 centimeters. It's nonsense. It should never have been entered as 0. It should have been entered as a blank. Nothing in it. Not that, not that. Blank means not available, not done. And stats software are all trained to ignore blanks. They do not include it and count it as a 0. Okay. Even if the calculation was right, some software will now tell you that you've actually got N equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because there are 12 non-blank cells. And this being left blank, and that one, and that one, and that one, and that one, then it would have correctly have said N equals 7. So that's the next point. So when I took those noughts and N/A's and all those things out, then the analysis and the calculation suddenly came right. You can see the mean is not 132, it's 167. The reason it's shot up is because we've left out 2 noughts that were really dragging the mean down. Right, so in summary, okay, those pretty little headings at the top have totally messed up our analysis. Okay, things like 2018 and totals and averages have been included quite erroneously in the analysis and have totally confounded it. Okay, these things have been interpreted as variable names, which has also totally messed things up. Okay, all these things were recognized as numbers, but those ones were recognized as words, as letters, as text, or strings, as it's technically called, and were left out of the analysis. That's got to be put right. And we saw that all these things, 4 years, 6 months, and greater than 50, and 204 months, have just been dropped from the analysis, which is a pity, because there's actually nothing wrong with that data point. But you must just have a standard rule as to whether you round down or round up. So you should have rounded that up to 5, if that's your decision. It was 4 years and 3 months, it should have been rounded down to 4, and so on. 204 months should have been converted to a rounded number of years, and then the analysis would have included those data points. There's nothing you can do about that, which is why you should not have recorded more than 50. You should actually have recorded the actual number of months of experience. Okay, consistency again. And then we saw how every misspelling and variation of these names was seen by the analysis as a different group. Consistency is absolutely critical. So you need to be absolutely meticulous about your data. As always, the more appropriately the data is captured first time round, the better. I think we've all had the experience that the more you have to manipulate your data, the greater the chance of errors creeping in. Okay, so now you're going through all these damn things, retyping them. But you get distracted at this point. So when you retype NMU, you actually write it down as UFS. And an error has gotten. If you collected the data by ticking UFS from the start, and it was captured in the spreadsheet as UFS from the start, then there would not have been the opportunity for that error. So when we talk about analyzing data, in actual fact, a lot of preparation should actually go into the way the data is captured long before you get to the analysis. You can see the problems in advance and capture the data, collect the data in a way which minimizes these errors. Right, so much for the way in which we present the data when we come to interpret it. Now let's talk about the actual interpretation. Right. The presentation of your data is critical. And I don't mean the way you present it to an audience or a paper or a lecture. It's the way you present it to yourself. It's got to be in a way which leads you to see into it, to see the trends. Okay, as I put there, your data has to talk to you. Data, what are you saying? Speak to me, is really what we are trying to do. I just see a raised hand. We better stop for a second and see what that's about.
Hi, Prof.
Yes, how are you?
I put my question in the chat, but actually I wanted to know how would you record a viral load of less than 40? Because it's not the same thing as 40. It's not the same thing as a 0. So how do you record that?
Right, that is always a difficult one, because by definition, there's no perfect way, because you are comparing an absolute number with a vague range, something that's not an absolute number. So what you actually have to decide is how you're going to do it. And then you have to describe what you've done and discuss whether it has possibly raised any errors. Let's say you decided to make it all 0. That would be acceptable. But then you would have to write, please note, undetectables were recorded as 0, and this will result in a slight reduction in calculations such as the mean, because it probably is actually 30 or 20, but it's been recorded as 0. There's really but nothing else you can do unless you decide to call less than 40, 40. And then you'll just have to explain that your actual result is slightly higher than the real thing, because some 20s and 30s have been recorded as 40s. But if you don't have too many of them down at that area, it's not going to make a major difference to your results. Recording it as 0 or as 40 when it's actually 20 is going to introduce very little error when you're comparing with numbers like 176,000 and 3.2 million, and so on and so on. What you can't do is just leave it out, because that is seriously going to distort your results. So I hope that sort of explains it. There is no ideal solution, and you just have to decide which is the most appropriate in the circumstances. And I'm not too sure which way is used most frequently, Vuyo. You'll probably know, from your reading. But in fact, just have a look at some good papers and see how they actually handled that. Does that help?
Yes, Prof. Thanks.
Okay, very good point there. Right. Okay, so the first thing I do when I analyze results, my own and students, is I put things in tables. Having calculated and done analyses on the spreadsheet, when we start writing results, we write them as tables. And we stare into those tables. As I've said, oh, table, speak to me. What are you saying? And there we try to look for the trends, for the explanations, for the interesting findings, and so on and so on. And I cannot stress enough, it's reiteration, reiteration. We look at those results, we argue about them, we think about them. It gives us an idea. We go back to the spreadsheet. Maybe it's pointed to a possible error, so we go and look for that and we correct it, and then we run the analysis again. Or maybe looking at those results, we get an interesting new idea. So I might say, Vuyo, did we actually analyze our results in terms of viral load or only in terms of CD4? And she may say, no, actually we didn't. So I'll say, right, let's go back and analyze it again. And surprise, surprise, we find that an interesting finding comes out with viral load that didn't come out with CD4. And we look at it some more and we discuss it some more and we get another bright idea again. I might say, Vuyo, we've analyzed it by race. We analyzed it by gender. Did we analyze it by race and gender? Is it possible that Black males behave differently to white females, even though in general Black and white behave the same and male and female behave the same? Is it possible that there are subsets that are different, as in Black male versus white female? That would call for a thing called a two-way ANOVA, and we would then do that study. Okay, so we would then return to the data and we would reanalyze it again. So I think that the mere fact that I'm talking about this gives you some idea that getting some data and making an appointment with the statistician and knocking on the door and sitting down and coming out with some stats is really not the way to do it. Because you need to look at the stats, think about it, go back, run stats again, think about it some more, repeat your analysis, go back and do a different type of stats on the same data. And of course, it's not usually possible to knock on the statistician's door on Monday and again on Wednesday and again on Thursday and again the following Monday and so on, as we go through these iterations upon iterations. And that is one of the reasons why you really should develop some comfort with statistics yourself. Not only so that you can reanalyze the data yourself, but so that when you speak to the statistician, you can actually engage in a discussion with them. There's a greater chance that by the end of the session, you've actually considered, thought through, and come out with more or less the sort of thing that you really want to come out with. Right. So it is not a case of do the experiment, collect the data, sit down for one afternoon, and the data has been analyzed, and then it's finished. Okay. Some very simple type studies that may be the case, but in most cases, it requires much more thought and insight and time, because as always, insights develop with time. As you look at the thing, you start to think differently. You see something that you missed first time round. Okay, right. Some of you will have seen this example before, but let me use it again. Okay, had a lovely colleague in Cape Town whose name is their first author, Dr. Mashiko Sechedi. Okay, this was her MEd project. I'd already come to Cape Town, at least to UKZN, and my colleague, late lamented, very sadly, lost at an early age, Prof. Bongani Mayosi contacted me and said, do me a favor, Mashiko is just, she's done nice work, a big study, and she's being rejected by journal after journal after journal. Maybe you can work with her. Maybe she can get it into the South African Medical Journal or something of that sort. So I said, fine. And I asked Mashiko to send me the spreadsheet. And we did exactly what I've been talking about. Okay. Now, she had analyzed a large retrospective database of patients at the Cape Town GI clinic with inflammatory bowel disease. That's Crohn's disease and ulcerative colitis for the non-clinicians. Many of them are treated with a class of drug called thiopurines, such as azathioprine and its prodrug 6-mercaptopurine. When used in high doses, as in immunosuppression in organ transplant cases, it's known to be associated with an increased risk of cancer. So Mashiko and her colleagues had set a very reasonable research question. Okay, is the use of thiopurines in the treatment of inflammatory bowel disease associated with an increased risk of cancer? That was the question. Forget the non-melanoma skin cancer. The question was an increased risk of cancer. And they analyzed it. All cancers, the answer was no. Right, so they tried to publish that in the journals, and the journals all said, ho-hum, boring. Okay, sorry, negative result, not interesting. We're not publishing it. But when I came to look at it again, I discovered something jumped out at me. Skin cancer. Okay, skin cancer was there, quite a lot of it, overwhelmingly in Caucasians. Now, about 20% of the sample was white, Caucasian. 80% were black and mixed race, okay? And yet 6 of the 7 skin cancers were in Caucasians. Now that, of course, is expected. We all know that white people get skin cancer because we are melanin challenged. Okay, but the relative risk for thiopurines was ×5. So if you took thiopurines, you were 5 times more likely to get skin cancer, but only if you were Caucasian. So this was a new finding. Okay, why hadn't it been seen before? Other people had done much larger database studies and got them published, which is why the journals weren't interested in this one. Well, the answer is Europe and North America have plenty of Caucasians, but they don't have any sun. So their Caucasians on thiopurines don't get melanoma or non-melanoma skin cancer. The developing world has plenty of sun, but no Caucasians. Okay? It's largely populated by people with dark skin, so they don't get skin cancer. And what we were seeing here in South Africa was these two coming together. A population that had quite a lot of Caucasians and a lot of sun. And now the risk became apparent. So the conclusion was there is an increased risk of cancer with thiopurines, probably only, but certainly especially for skin cancer, but only in your Caucasian patients, and then only if they live in sunny climates. So the take-home message, if you're in Europe or North America, you don't have to worry about skin cancer. You can just go ahead and treat your patient with azathioprine. If you live in India or Africa and your patients are black, exactly the same applies. You can go ahead and treat them with azathioprine without a risk of cancer. But if you live in Africa and you're dealing with a large number of white patients, then you have to be careful. They are at risk of skin cancer anyway, and the risk is 5 times increased if you treat them with azathioprine. So you better monitor them very, very carefully going forward. And so this now got published in a very decent, reputable journal. The reason was the data spoke to us, and out came some interesting things in that data that were actually not part of the original research question and that our other colleagues had overlooked because they just did the straightforward analysis. How many cancers in those who were treated, how many cancers in those who weren't treated, and overlooked this interesting finding. So that's a classic example of how you need to speak to your data, or perhaps allow your data to speak to you. Study it, think about it, argue it, reanalyze it, run it again. ask a new question. I wonder if skin cancer is different. I wonder if race is playing a role in skin cancer. These were not things that were ever thought of at the start of the study. Right, that's the first point. Second point here is don't jump to conclusions. Clinicians are terrible at doing that, okay? This is a very interesting study for a PhD done by my student, Dr. Darrell Wood, a number of years ago, who was the emergency physician at Ngwelezana Hospital in Pangeni, who was an expert and extremely interested in snakebite, okay? This is the ages of patients who presented to him having been bitten by a snake. So far, so good, largely in that 15 to 20 age group. But he kept coming out with this very fundamental statement. Babies are at particular risk of being bitten. The Mozambican spitting cobra, Mfezi, has got a real weakness and fondness for getting into infants, babies' beds and biting them. He said this repeatedly, and all his colleagues said this. The implication being that the number is just lower because there are fewer babies. So we analyzed it properly. You may have seen this. This is called a radar plot. This is the actual age distribution of the population. I looked up the census data for northeastern KZN. For example, before the first year of life, that's 15% of the population. Okay, 0 to 4 is 12% of the population. 5 to 9 is 15% of the population. Sorry, we should be looking at the red line. 5 to 9 is 11% of the population. And then we did the same for the snakebite patients. And you can see that the graph is not the same, it's distorted. The 10 to 14 group is twice as likely to be bitten, okay, as expected for their age, because they're only 11% of the population, but they are 21% of the snakebite population. And the infants are only half as likely to be bitten as expected for their age. So in fact, those confident statements from Darrell and the rest of the snakebite community were actually quite wrong. Mozambique spitting cobras don't have a particular desire to go and bite babies. In fact, they're half as likely to bite babies as what you'd expect from the population. But what they really do like is biting 10 to 14-year-olds. And of course, that makes sense. That's at the age at which the kids are walking across the fields to go to school. The girls are going down to the rivers to collect water. The boys may be out in the field herding, kicking a football around, you know, in the open, etc., etc. Makes perfect sense that that is the group that's most at risk of being bitten. So again, you see, just by looking at the data and analyzing it differently, we were actually able to debunk a misconception. And better still, able to prevent Darrell Wood from making an incorrect statement in his thesis. Right, so careful analysis of data includes using the right analyses. It's just a matter of doing the mean and the standard deviation accurately, or whatever it is. Okay. Same study. Are older people more likely to be envenomed? Now, what I learned from him is that snakes, in fact, quite often do what's called a dry bite. They bite you, but they don't actually inject the venom. I think venomous snakes realize that there's an energy cost to making venom. So they try to hang on to it for the time they really need it, which is when they're trying to kill their prey so that they can eat it. So in fact, in up to 0.5% of all bites by a venomous snake, there's no venom injected. Now, looking at this data, it rather looks as though old people are much more likely to get a venom, a genuine bite. And you can start speculating why that might be so. Until you do the stats and you do the confidence intervals, they're totally overlapping. So in actual fact, that apparent difference is meaningless. What could be 80% could be anywhere between 45% and 95%, totally overlapping all the others, including the third decade, where it could be anywhere between 42% and 50%. So no statistical difference at all. This can all be artifactual. The reason why this confidence interval is so wide, of course, is because there are so many fewer subjects in this group. Many more subjects in the lower group, therefore smaller confidence intervals. So again, don't jump to conclusions. It requires statistical analysis before you can do so. Right, so what you're getting at is in interpreting your data, don't lose sight of your research question, your hypothesis, your aims, your objectives. The question always had to be, I found an answer, but to what? What was the question for which I've got an answer? If you don't know what question you are answering, then your answer doesn't make any sense. Those of you who've heard me talk before know that I go on and on and on and on about having a research question that you thoroughly understand. A hypothesis possibly, aims, objectives. So the first question is, what question did I set out to answer? But as I've suggested, very often, particularly in clinical research, because it's messy, you may actually find that without meaning to, you've actually answered a different question. The question we set out to answer was, are thiopurines associated with cancer? The question we seem to have answered is, are thiopurines associated with cancer in light-skinned people in a sunny climate? Okay, that's actually the question we did end up answering. Maybe serendipitously, we didn't set out to do it. Right. So that is an excellent thing to do. However, I must just warn you that people quite rightly require convincing when you change the question after you get the answer. Okay, because it is just so easy to come up with a question that just happens to fit the data, okay, and give you a different answer. So you really have to justify very strongly why at the end of the study, the research question and the hypothesis, the aims, objectives aren't quite what they were when you set out, okay, when you submitted to your ethics committee. And that frequently happens particularly in medical, perhaps not so much in biological research, okay? Nothing wrong with that, as long as you're absolutely honest about it, open about it, state it in your papers and your thesis, so that people can check your thinking and see whether what you have done seems reasonable. And it's not a case of you saying, whoops, nothing came out there, so let's search around until we find something that's statistically significant. Okay, so be aware of that. You can't just pick and choose data that gives you something nice. Well-known trap. So what I'm really saying is honesty and transparency. Honesty and transparency in pruning your data. Okay. This is a common mistake. And unfortunately, it's something that is not infrequently deliberately done, and it's dishonest. Okay. So I have a hypothesis, okay, that females have more car crashes than men. So I do the study and it turns out to be the other way around. So I go back and have a look, and I find if I leave out all females that live in Durban, okay, suddenly the answer goes the other way around. Maybe because, you know, females who live in rural areas have not been to the same driving school and have not had the same driving experience in a busy city as the ones who live in the city. So now I go and restrict my female population to those who do not live in the city. And now, rah, 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 I've suddenly got the answer I wanted. Not acceptable. If you decide to leave out all females who live in the city, you have to state in your paper that you did so, why you did so, and discuss whether this might have distorted your results. Honesty and transparency in choosing your results or calculations. When results hover around the statistical level, It sometimes happens that you find that your t-test comes out as p equals 0.05, and your Mann-Whitney u-test comes out as p equals 0.06. There's a horrible temptation to choose the one that fits, that gives us the nice, significant result. You should be honest about that and state, okay, and justify why you used one rather than the other, okay? If only to flag and say, we suggest that this result is interpreted with caution, okay, as it is of borderline significance, and indeed not significant by the t-test, only by the Mann-Whitney. Right. So what I'm saying is you can more or less do whatever it takes with your data to obtain the most scientifically valid result. Not the result that looks best or looks most exciting or suits your prejudices. But you can see there the ... we've got it qualified. Provided you are completely honest and transparent about what you have done, and you explain and discuss your reasoning and how you came to analyze and interpret your results. Okay, you're completely honest and transparent in the way you did it. Most important thing. I've said just about every thesis I've dealt with. At the end of the day, the aims, objectives, and methods and results that we've handled, objectives, etc., are not actually what was set out, because you get wiser, more experienced as the work unfolds. You see what's working and what's not working. No problem. What we then do in the thesis, we explain that. At the start of the study, these were our aims and objectives. As the study unfolded, it became apparent that a more meaningful line of research would be the following: modified aims and objectives. And this is what we did. So it's up there, up front, and the examiner can see. And if you've been reasonable and it was a sensible thing to do, your reviewers and examiners will agree with you. There'll be no problem. On the other hand, if you don't do that, then they will be justified in thinking that you yourself don't even know that you haven't actually answered your own objectives, or worse still, that you are trying something dishonest and sneaky under the table. Right. Now, I just want to end up with an example. This is actually quite horrifying. Most of you are well aware that there's been ongoing debate for 2 years now about whether the simple, cheap, safe, anti-parasitic drug called ivermectin is actually useful for preventing and treating COVID-19. And numerous claims have been made that it's highly effective, not a little bit effective, but people have been talking about a 60% reduction in mortality. Instead of 10 people dying out of a group, only 4 are dying. Instead of 100 dying, only 40 are dying. Huge claims have been made for it. And this was a recent such study, a citywide prospective observational study, a huge sample size, 223,000 subjects. Okay? And it found a major reduction in infections and in mortality. Sorry, somebody just switch off the microphone. Okay, in subjects. Right. I actually watched a very interesting YouTube video, and this is not some polemic. This is a very sensible biomedical man who has a YouTube channel and is very, very, very scientifically rigorous. I'm totally convinced by what he says. And he went through this paper dissecting it. And this is the sort of thing he found. Okay. So the authors claim there were fewer infections after the city offered voluntary ivermectin to all its citizens. So they started a program. Anybody who wanted to could report to a clinic, would be told what to do, would be given a prescription for ivermectin, and could come back every 2 months to get more. Okay. And after that, there were many fewer infections, suggesting that it worked. But he then went and looked at the national data, and guess what? This project started just before the crest of a COVID wave. And throughout the country, simultaneously thereafter, the rates of infection went down throughout the country, not only in the city that had started giving ivermectin to people. Okay, So the authors had either missed that or had deliberately ignored that. They should have controlled by looking at other cities that didn't have such a program and make sure that the rates weren't declining at the same time. So bang, that's discredited. Then, of course, they reported that outcomes were better in the ivermectin group. But he found a municipal report from the Department of Health that introduced this program, complaining that hardly anyone who started off on the ivermectin actually kept it up. By the third visit, they were down to 9% of the people who had signed up for the program. So most of the people that they stated were on ivermectin were actually not on ivermectin at all. So you're actually comparing a group that's not taking ivermectin with another group that's also not taking ivermectin. So what's going on there? Discredited. Okay. Now the next thing is, if you look at the title, it looks very fancy, very scientific. It's, by the way, it's not prospective, it's actually retrospective. Okay. People were given it prospectively, but then was analyzed retrospectively. Okay. And they tried to match the people because they weren't randomized. Okay. So they tried to match people so that the two groups, well, were matched. Okay. So they matched them for age, weight, comorbid illness, but those are not the critical risk factors for infection. The critical risk factors for infection are not wearing a mask, living in crowded conditions, socializing with large numbers of people, not wanting to be vaccinated, etc., etc. And we all know that those things are strongly bound up with socioeconomic factors. Okay? At the very least, the people who take themselves off in response to an invitation to a clinic to get ivermectin are likely to be those who've got the time off, can take the time off work to do so. The people are better educated and understand these things. The people who have a car to drive to the clinic. Okay. And the sort of people who are interested in maintaining the health of ivermectin are probably also the people who are interested in maintaining their health by avoiding overcrowding, wearing a mask, etc. And that was not controlled for. So they controlled for these relatively unimportant things, but they did not control for the most highly important factor. Okay, the socioeconomic and behavioral factors that determine your risk for infection. So bang, again, there goes their argument. They must have become wise to the fact that many of the ivermectin group had not taken ivermectin at all. So they've subsequently published a preprint, in other words, a paper that they say they're going to get published, but at the moment it's just there for everybody to read before peer review. And now, looks quite sensible on the surface. They've divided the ivermectin group into those who are 100% adherent. Okay. And they've compared those with the control group. Now, that sounds very sensible. How did they define 100% adherence? People who took the total number of pills that would be taken by somebody from the start of the study to the finish of the study. Okay. They worked out, let's say, for example, you're supposed to take it every 2 weeks, 2 pills. There were 6 months of the study, so you should have taken 24 pills. So they defined full adherence as anybody who had taken 24 pills. Absolutely incomprehensible. Look at the top line there, okay? Those little vertical lines are people who died. So the red group at the top is the control group. So somebody died, after a few months. It was many more, but I've taken 8 deaths there. Now look at the ivermectin group at the bottom. Let's say it was, for example, identical. Aha, in order to be labeled fully adherent, you had to take 24 pills. Well, unfortunately, if you got your COVID after 2 months, you hadn't taken 24 pills, you'd only taken 8. So they dropped you from the analysis. If you got your COVID after 6 months, Well, sadly, you'd only taken 12 pills, not 24, so you're regarded as not fully adherent. So at the end of the day, they discarded those 7 and said there was only 1 death in the fully adherent group. Now we're comparing with 8 deaths in the control group. And you can actually see how that is, well, it's a statistical lie, isn't it? So absolutely makes the point. And then just to go back, cherry on the top, when this paper was first submitted, it said the authors all state that they have no conflict of interest. When people wrote to the journal complaining that this was just not true, they were forced to write a correction with an extensive list of conflicts of interest. Some of these people were being paid by the makers of ivermectin. Others, you may recognize some names here, have staked their lives and their names and their reputations in the last 24 years on claiming that ivermectin works. And some of them are running clinics where they are attracting all the people who are desperate for some sort of cure and are coming to them because they dish out ivermectin. So they've got huge conflicts of interest, which really raises the question, are these honest mistakes in the analysis of this data, or is there actually something more sinister going on here? Right, so that is it for today, and we're available for some questions, comments, statements, discussion. Right, thank you. I'm going to stop the sharing. Chat, nothing there. Right, see on, right. The skin can just open my eyes to mistakes I've been making in my data analysis. Well, all of us. How do our supervisors check that we've been honest with our data? They must check. They've got to check your data. They've got to know your data. Okay. They can't just take your word for it. Remember, I doubt that many of you have actually been dishonest, but you may well have made honest mistakes. Okay. Either genuine mistakes, like unfortunately deleting a few lines. Excel is very, very easy to delete data by mistake without knowing you've done it. Another horrendous thing Excel does is sort some of the data, but not all of it, so that the wrong CD4 counts end up next to the wrong patients and so on. Okay, those are actual mistakes, but then they also need to check that you haven't made honest mistakes. No, like deciding, for example, to say all undissectable viral loads are replaced with a blank, which means not done. Completely different from almost 0 and not done at all. So your supervisors have to know your data well. And if the COVID pandemic and the literature and the ivermectin debate has shown anything, is that every single author has to understand the data. Okay, there's nothing more embarrassing than it's happened repeatedly now, of senior people having to say, I greatly apologize. I was asked to come in on this paper and help with the discussion. I had not looked at the data myself, and I did not realize that it was fraudulent. It's been happening repeatedly now. Okay, so every author has to understand the data. And if you suspect there's anything dodgy with it, refuse to have your name on the paper. Do not put your name on papers where you have a suspicion and cannot check that all is not as it seems. And it's gone one step further now. And we as the scientific community have realized that we can't even trust what other authors are saying about their data. It's rapidly reaching the state where all the data has to be available, not just to the reviewers, but to the entire community. So that I, for example, could decide, not knowing Mpoi, maybe I'm working the other side of the world, Mpoi Mketa, who made a comment here, okay, that there's something funny here. And I can go on the web and get her entire data set, anonymized, of course, for confidentiality, and can reanalyze it myself and say, hold on, why did you exclude all the males? When I rerun the analysis, including all those males, suddenly I get the opposite interpretation to what Mpoe published. So there's now a very strong movement that if you're not prepared to make your data freely available to everybody, then it probably means you've got something to hide. This has been very, very, very much happening with ivermectin. And several of the initial huge studies which suggested that ivermectin was strongly effective. When finally people got access to the data and looked at it, they noticed weird things. Patients that were recorded before the study started. Okay. Patients where patients 6, 7, 8, and 9 seem to have the same results as 1, 2, 3, and 4, and 11, 12, 13, and 14, and so on. In other words, clearly people had just copied and pasted data into numerous rows. In other words, they were making up the data. They were too lazy even to try and be clever with it. Okay. And there are now forensic specialists who've got it down to a fine art of going through data sets and picking up the signs of fraud. It's exactly the same way they pick up fraud in the books, accounting books of companies and things. For example, it's known that, I don't know why, but in numbers, you don't get equal numbers of 1, 2, 3, 4, 5, 6, 7, 8, 9. So if they go through it and they find that the number 1 and 9 and 8 and 7 all come up equally often, it's actually a sign that fraud is at work. Because the natural process, there would be a few more 3s and a few less 1s, that sort of example. So it's becoming sadly very, very clear that the scientific literature is rife with misinformation, either honestly done but misinterpreted, okay, or in fact dishonestly interpreted, as in that example I've just used, where at the most charitable, it was extremely unscientifically badly interpreted. At worst, dishonestly. We hope not. Okay. And one doesn't know. So I'm not making accusations. And thirdly, outright fraudulent data. Okay. So we've strayed a little bit from how to interpret data, but it's all absolutely the same. And I think at this stage, you'll also see the very strong commonality or crossover with how to read a paper, which is really, I think I made a statement when I gave that talk. In order to read a good paper, you actually have to be able to write a good paper. You have to know what mistakes to avoid when you write in order to recognize those mistakes in somebody else's paper when you read it. Okay, so thank you for that one, Zahra. Any other comments? Feel free to open your mic and just speak if you don't want to write. Okay, so that seems to be all, so we'll leave it at that. Just to say that if anybody had already noticed on the web that we advertised the qualitative research thing for later this month, Maud has discovered that there's a public holiday in the middle of it, so we've moved things back a week later. I've spent a bit of time in the last few days working on the website and just trying to get that calendar and program a bit more user-friendly and make sure it's up-to-date and accurate. So please just look at the website frequently and look at the updated programs that are published there. Thank you, and bye-bye.